All right, greetings, guys. So we're going to continue on with the next installment of Chapter 5, this beast of a chapter. Hey, a couple reminders for you. Keep on keeping on with your biogeochemical cycles, all right? It's a fairly hefty portion, and, we'll tie back into them occasionally with some of the other stuff in this chapter, but they are kind of like their own little sort of independent piece, and if you ignore them, they're not going to go away. So keep spending some time, maybe once a day for 5-10 minutes, just going back over the ins and outs of those cycles, okay? And then, of course, and I tell you this all the time, I'm just going to keep on saying it several times a week, the whole year, is to keep up with your reading, all right? So you guys should be taking your notes at home, watching lectures, but you should also be keeping up with the reading, right? So after this lecture, you should be up through page 110 for Chapter 5, which is like the first, 18 pages or so, okay? So, in class, we're talking a little bit about some of these things. Factors affecting local or regional climate. Latitude, of course, is going to affect the intensity of the sunlight. It affects, so the sun is going to affect the prevailing winds. That's horrible writing. It's also going to affect seasonal variation, right? All right, we got prevailing winds, right? So that is the general direction from which winds come, right? And that is a function of your latitude, right? Along with those Hadley cells we talked about. Where do we have rising air creating low pressure? Where do we have sinking air creating high pressure? And so on. Prevailing winds are going to determine kind of precipitation patterns as well for us. And we'll get to that a little bit more in just a minute. Proximity to water. So that is that specific heat bit we spent the lab doing, and actually a couple of days trying to follow up on. How does your proximity to water affect the climate? All right, so in general, if you're near really large bodies of water, right, you're going to have more mild weather. You won't heat up as quickly, nor will you cool off as quickly. And then, of course, topography, which is something we haven't talked about much yet. This deals with things like, you have really high altitude. That's, of course, going to affect your precipitation type. Generally, you get a little more precipitation in the mountains. But also where you are relative to the mountains and your prevailing wind direction. That's going to come up next. All right, so we have this phenomenon in nature we call rain shadows, all right? And so some terminology we want to get used to, the windward versus leeward side. So the windward side is just the side of the mountains that the wind comes from, whereas the leeward side is just the other side of those mountains. So here in the mid-latitudes, right, we have winds coming in generally from the southwest. So the windward side of our mountains in the U.S. would usually be the western side of the mountains. All right? So if you look at patterns in the U.S., right, the west side of mountains tends to be the wetter side. The east side of mountains tends to be the drier side. And that's because of this rain shadow effect. And essentially what happens is mountains force moist air upward, right? When they're forced upward, that seeds cloud formation and drops precipitation. So that windward side pushes the moist air up to the mountains. Mountains force that air up, right? That causes cloud formation and precipitation then to fall on the windward side of our mountains. Now, it's important to point out that if I went to a different latitude, where maybe my winds came from the east, the wet side of the mountains would be the east side, not the west side. Okay, so windward is not a synonym for west. It's just the side the prevailing winds come from. All right? Now, so rising air creates precipitation. Sinking air creates dry air. All right? And that's an important phenomenon, not just in a regional area with rain shadows, but that's what we see happening with our Hadley cells, right? At the equator, we have rising air. Equator, we tend to get lots of moisture. That's why our tropical rainforests are found there. Likewise, at 30 degrees north and 30 degrees south, We have sinking air, which tends to be dry. So our big, like global deserts, like the Sahara, for example, are found near that 30-degree north or south line of the equator. We have that dry, sinking air. All right. So let's take, for example, oops. Whoa, what am I doing? What am I doing? Boom. All right, so boom, boom, boop, 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 boop. Okay, so there's an ugly picture of Washington State. Now, in Washington, we kind of have rain shadow effect happening in a couple locations. So first of all, here's our Cascade Mountains, right? Running down the central western part of the state, right? We also have some little mountains right here up on the Olympic Peninsula called the Olympic Mountains, okay? Now, some interesting rain shadows happen here. Now, of course, we all know that in eastern Washington versus western Washington, where's most of our rainfall, right? Over here. That's because our prevailing winds come from the southwest. They hit the Cascades, and we get lots of rain over here in western Washington. Okay? So, Walla Walla being over here, Seattle up over here, no major difference in our latitude here, right? It's not because we're getting, we're closer to that 30-degree north mark where we have deserts. It's because we have this sinking air coming down the east side of the mountains. It makes the east side of the mountains a little drier because the east side in this case is the leeward side, whereas the west side is the windward side. Windward side of the mountains tends to get more rainfall. All right? Now, another cool little rain shadow effect happens right up here on the Olympic Peninsula. All right, little town up here called Sequim, spelled Sequim, right? So in Sequim, Washington, they get about the same amount of rainfall as Walla Walla, interestingly, all right? So over there in western Washington, out on that Olympic Peninsula, where we actually have rainforests, Sequim, Washington, gets about the same amount of rainfall as Walla Walla. Now, as you move west from Sequim, Washington, over here on this side of the mountains, we have a little town called Forks. Okay, Forks, Washington, recently made famous because of the Twilight series, right, of books, right? In Forks, Washington, right, they get 100+ inches of rain a year in that just really short little distance between Sequim and Forks, Washington. We get a huge difference in rainfall. In fact, as you go west from Sequim, so from Sequim west, you get 1 inch of rainfall added per mile. All right? So if you go from Sequim to, let's just say, Port Angeles, right there, near Sequim, it's about a 20-mile drive. You go from about 19 inches of rain in Sequim to about 40+ inches of rain in Port Angeles. About 1 inch of rain added per mile west there. So it's kind of a cool little climate phenomenon. Just wanted to share that with you guys. All right. So first of all, making sure we understand a differentiation in these two terms, weather versus climate. So weather is referring to the conditions in the atmosphere at any given place and time, right? So when you want to know what the weather is, you look outside. What's the temperature? What's going on? Okay. Whereas climate is a more average term. And I hope by this point in your guys' careers in science, you kind of understand that difference in terminology. So weather is a given place and time. What's it going on right now? Climate describes what it's usually like, maybe. So if we were to describe the climate in Walla Walla, we would say, oh, Walla Walla has hot, dry summers and cool, moist winters or something like that. That doesn't mean that every day in the summer is hot and dry, or that every day in the winter is cool and wet. Okay? So that's our fundamental difference. The book, actually, I'm not going to spend much time on this, has a really cool diagram of kind of the various climates and so on. I encourage you guys to take a look at that. But we are going to move on to severe weather. Right? So some severe weather types that we experience right here in the U.S. are tornadoes. So tornadoes form under very different conditions. than hurricanes do. All right. Tornadoes are much smaller scale, and they have much higher wind speeds, actually. All right, so they form under what they call supercell conditions, or frontal conditions, where you have a mass of cool, dry air colliding with really warm, humid air. So typically, to get a supercell formation like this, you have to have a really, really warm, humid air mass. That's why they form more often over places like Oklahoma and Texas, where they have that kind of Gulf air mass there. Okay, that's really warm and humid. Right, and they get these frontal systems of cool, dry air that kind of force that air upward. And they get a really, really rapid formation of these huge, huge, billowing, towering thunderstorm clouds they call supercells. All right, and when that happens, it produces a really, really strong updraft. And with kind of upper atmosphere winds, it creates the spinning, right, under a cloud. And when that spinning air hits the ground, it's then called a tornado. All right, they can get speeds in tornadoes up to 300 miles per hour. That's enough to send a piece of hay or a piece of straw right through a glass window without breaking it. It's crazy. Tornadoes are really, really destructive over generally, though, a relatively small area compared to things like hurricanes. All right, so probably much more drastic destruction, but in a more localized area. Okay, these tend to happen in the southeastern United States. They occasionally get their way up to the north central United States, and there's even been some random little reports of tornadoes touching down here in Washington State, but they tend to be pretty wimpy compared to those monster tornadoes they get in the Midwest. All right, and like I said, their width is going to range anywhere from 1 meter to 3.2 kilometers for the really big tornadoes. All right. Now, to contrast those a little bit, also weather events. So again, we're talking about what's going on outside at any given time are what they call tropical cyclones. Now, tropical cyclones are giant rotating tropical storms, and they form over warm surface waters. Okay, so ocean water that's been warmed up after the summertime. All right. So to call it a cyclone, they have to have wind speeds of more than 119 kilometers per hour. Okay, and strong winds pick up moisture over warm surface waters. They spin due to the Earth's rotation. So there's the Coriolis effect coming into play. All right, so they are big enough to actually be impacted by the Coriolis effect, and the spin kind of causes this upward spiral of clouds. So associated with our tropical cyclones is heavy winds, right, and lots of rainfall associated with it as well, right? So this is actually a picture of Hurricane Katrina. Now, what we have is a little low pressure zone right there at the eye of the hurricane. You may have heard that term before, okay? So as the air rushes in, right, from higher pressure toward the lower pressure, the Coriolis effect, because this picture is showing in the United States, we know this is northern hemisphere, Coriolis effect is going to deflect that air to the right. Okay, and likewise here, it's going to deflect that air in this sort of spiral pattern like that, right? So we get a low pressure area caused by a rapid uplift of air that forms over really warm waters, right? And they can cause crazy damage, right? So hurricanes, by the way, form over the Atlantic or Northeast Pacific, typhoons over the Northwest Pacific, and cyclones over the Pacific or Indian Ocean. But they are the same thing. They're the same type of storm. They form in the same way. We just give them different names based on their geographic location. All right? Now, major storms in the last 15 years, right? There's actually been a lot of them. These are some kind of more commonly referred to ones. So Hurricane Katrina, which most of you guys are too young to remember, really, really widespread damage in the New Orleans area. Right? It was a category 4 hurricane that came and flooded New Orleans. In 2012, Hurricane Sandy, which you guys should remember, not that long ago, came up and hit off the coast of New Jersey. It was a category 3 hurricane that kind of mellowed out, but because of the way it hit landfall, it did some widespread damage. The second most damaging storm in U.S. history, second behind Hurricane Katrina. Now, not in the United States, formed out over the Northwest Pacific is Typhoon Haiyan, which hit the Philippines. Okay, sustained winds of 190 miles per hour. We're talking tornado force winds. Okay, but remember how I said tornadoes cause kind of localized damage and they're relatively short-lived. These are nearly tornado force winds covering, hundreds to thousands of kilometers, and it just came and stuck. 6,300 or more deaths in the Philippines. Actually, a year after, we're still finding bodies buried in the rubble. Kind of crazy. All right, and that is going to be it for the day. So I told you I'd keep this one a little shorter, a little over 16 minutes. All right, so make sure you guys do the follow-up reading that goes along with this.